Um, Hello everyone. I am Dr. Ramesh Panickar, an associate professor in the chemistry department at IIT Kanpur. I would continue to talk to you about the reactions of haloalkanes and haloarenes, the chemistry of haloalkanes and haloarenes. So these are topics that are covered in the unit 10 of NCERT chemistry textbook for class 12 students. So in the previous class that I have already talked to you about various classifications of haloalkanes and haloarenes, how their nomenclature is given, how they are named, and what are the common names of these compounds. We also looked at certain examples of this class of compounds that are found naturally and also some of them synthetic, and we discussed that these are highly important class of compounds that find a large number of applications in daily life. Then we proceeded on to say about the nature of carbon halogen bond, and which is the reason behind most of the chemistry that we would be discussing in the coming 2 classes or so. And then I also proceeded to discuss about the preparation of haloalkanes from simple starting materials, and I have discussed only one of the points, that was preparation of these compounds from alcohols. So I would start off by rewinding a little bit on the preparation of haloalkanes from alcohol, so that we get continuity with respect to what we have been discussing. So to start with, I would talk about preparation of haloalkanes from alcohols. So as you can see in the screen here, if you take an alcohol and treat it with a hydrohalic acid, we would get a haloalkane plus water. Some of these reactions are catalyzed by zinc chloride, a metal chloride. So the purpose of using zinc chloride is to facilitate the cleavage of the carbon oxygen bond, and then the installation of the halogen bond onto the carbon atom from where the hydroxy group has left. The order of reactivity for this class of compounds is generally tertiary alkyl halides reacting faster than secondary, reacting faster than primary. So therefore, the reaction of primary and secondary alcohols to be faster, it is quite essential that we use the catalyst that we have already discussed. So zinc chloride in this case acts as a Lewis acid that coordinates with oxygen and facilitates this reaction. It is to be noted that this reaction is not possible for haloarenes, just for the fact that the bond between oxygen and carbon is quite strong in phenols, so we cannot prepare haloarenes using this particular method, whereas this is only applicable for the synthesis of haloalkanes. Now the alcohol group, the hydroxy group, can be replaced by a halogen atom in the presence of acid. So this is the essence of the reaction. So the acid that is used in this case can also be an acid different from hydrohalic acid, provided that we also supply in the reaction mixture enough number of halide anions. So we can carry out this reaction with sodium iodide or potassium iodide. In such cases we will have to use another acid so that water can be removed from the alcohol. So these are 2 examples of that kind, and then I went ahead and said that phosphorus trihalides or even phosphorus pentahalides can be used for making this reaction, and some of the phosphorus trihalides like PBr3 and PI3 need not be added directly into the reaction. Instead they could be prepared in the reaction mixture by the reaction of red phosphorus with the corresponding halogen molecules. So this is something that we have already discussed, and the most important point when we were discussing the synthesis of haloalkanes from alcohols was the fact that when an alcohol is treated with thionyl chloride SOCl2, that gives the haloalkane along with sulfur dioxide and HCl. So these 2 are the byproducts that are formed in the reaction, and interestingly these are gases. So whenever we carry out the reaction of alcohol with thionyl chloride, it is not only that the reaction is an effective one giving us the haloalkane, it also produces byproducts which are gaseous that will escape from the reaction mixture, allowing us to isolate the products, in this case the haloalkanes, quite easily. So this, for practical reasons, is one of the easiest reactions. So now I will go further and I will talk to you about other methods for preparing haloalkanes. So the second method that I would like to talk to you is about the preparation of haloalkanes directly from hydrocarbons. So you would have to realize that by hydrocarbons we mean compounds that only have carbon-carbon and carbon-hydrogen bonds. So in for this class of preparations we will have to break a carbon hydrogen bond and install a carbon halogen bond. So, that is what we want to do. So, this is normally done, this is something that we can do. So, this can be done by taking an alkyne. So, in this case I have represented the alkyne as RCH3. So, let us assume that R is an alkyl group, could be bigger, attached to a CH3, a methyl group in this case. Now, if it is treated with chlorine or bromine, it can be either chlorine or bromine, in the presence of UV light or a lot of heat, it can generate RCH2Cl, that means the corresponding chloroalkane plus HCl. So, when we look at this reaction as I have written here, as the look at the equation, it is quite evident that this is a very effective reaction, because we are taking an alkane, breaking a carbon hydrogen bond and installing a carbon chlorine bond. So, nothing could be simpler. However, it isn't that easy. So, in order to understand the reaction, I will go into the mechanism of this particular reaction. So, this whole reaction happens because halogen-halogen bond, as in chlorine molecule or bromine molecule or even I2, is not very stable. So, therefore, if you provide enough energy either in the form of light or in the form of heat, the halogen-halogen bond breaks. And once the halogen-halogen bond breaks, it does not break in an ionic fashion. Each of the halogen atom retains its electron. So, they form free radicals, which are normally represented by putting a dot over the halogen atom. So, in this case I can show that Cl2, which is chlorine molecule, absorbs light energy and becomes 2Cl dot, where the dot stands for that extra unpaired electron that is present in the radical. So, now this is a chlorine atom. So, there are two chlorine atoms that are formed from chlorine molecule. Now, the chlorine atom then reacts with the alkane, so in this case RCH3, and it abstracts a hydrogen. So, because chlorine is extremely reactive, once we have atomic chlorine or chlorine free radical, it is extremely reactive. So, it is able to abstract a hydrogen from the alkane, thereby giving us RCH2 with that dot indicating that it is another radical. So, we create an alkyl radical plus HCl. So, HCl comes out and an alkyl radical is created. Now, this alkyl radical would then react with chlorine. So, what do we have in the reaction mixture is chlorine molecules plus alkane. Now, we radiate with light. So, the chlorine breaks first into two halogen atoms. One of the halogen atom then abstracts a hydrogen that gives us an alkyl radical plus HCl. Now, this alkyl radical that has formed would react with another chlorine molecule, and in this case what it does is it breaks the chlorine molecule into chlorine atoms and bonds with one of the chlorine atoms and generates a chlorine radical. So, you would find that as a result of this reaction we have actually got a haloalkane, a alkyl chloride, plus a chlorine radical, which will go directly into this step and continue to do what it has been doing. So, in effect what we are doing is, in the second step we are regenerating a chlorine atom, a chlorine radical that can continue the reaction further. So, it just gets propagated. So, this is how this whole reaction happens. So, if you would like to see what exactly is the mechanism of the reaction, all we need to do is sum up these two reactions that I have written here, these two equations. So, it would amount to be RCH3 plus Cl2 giving you HCl plus the corresponding chloroalkane. Now, so this is the mechanism of the reaction. I told you that although it looks simple, it is not an easy reaction. It has its own problems. So, let us see what are the problems here. So, once you have a chlorine radical, the radical can pick up any hydrogen from the alkane that is present. So, normally alkanes would have multiple number of carbon hydrogen bonds. So, radicals such as chlorine radical will not be able to distinguish between these various carbon hydrogen bonds. So, therefore, what happens is it starts to pick whichever hydrogen is immediately available. So, therefore, we end up getting mixtures of products. Not only that, the product that has formed in this case, which is RCH2Cl, also has additional carbon hydrogen bonds. So, the chlorine radical can further react with the product that is already formed and lead to multiple halogenations or multiple chlorinations in this case. So, this is one of the major disadvantages of this reaction. So, their synthetic application, although the reaction in an equation looks simple, is not much. So, this is one of the limitations. So, just to emphasize this point, I have another example here. So, I have butane which is being treated with chlorine and UV light. So, I get two monochlorobutane products. So, if I assume that only one of the hydrogens are picked, even in that case I can get one chlorobutane and two chlorobutane. These are monochlorobutane. Additionally, I can also have polychlorobutanes where there can be more than one, that is 2, 3, 4 or 5 hydrogen atoms replaced with chlorine. So what we get at the end of the reaction is a mixture of products where there are these various isomers of monochloro, dichloro, trichloro and so on compounds present which cannot be isolated that easily. So therefore this looks like a good reaction, but it is not very useful in terms of its synthetic applications. Now the third reaction that I would talk to you about the preparation of haloalkanes is the reaction of alkenes with hydrogen halides, HX. So this is probably a reaction that you studied when you have studied the reaction of alkenes. So alkenes add on to HX. So in this case H plus and X minus, as one would ionize these molecules to. So it reacts with alkenes to give compounds that have a hydrogen and a halogen added across the double bond. So this reaction then gives a new carbon halogen bond, so therefore haloalkanes. So I have an example here which is propene. When propene is treated with HI, we get the corresponding iodopropane with iodine attached to the first carbon atom, that is 1 iodopropane or 2 iodopropane. You would find that 2 iodopropane is the major product in this case, and this is something that you have already studied, because reaction of unsymmetrical alkenes such as this, that means when you have a double bond that are differentially substituted on the 2 carbon atoms that are involved in the double bond, then the addition reactions of such molecules happens in such a way that the halogen atom gets itself attached to the most substituted carbon atom. That is, there is a preferential formation of more substituted halo compounds. This rule is Markovnikov's rule, which you have studied already. So it simply tells you that the products of such reactions usually result from the most stable carbocation that one can imagine. So in these cases you would already know that the most stable carbocation is a tertiary one, followed by a secondary and a primary. So in the case of the reaction of propene, the carbocation, if at all formed, would be the one that is having positive charge on the secondary carbon atom, that is the carbon atom in the middle. Therefore iodine gets attached to the second carbon atom, giving this as the major product in this particular reaction. So this is so the addition of hydrogen halides to alkenes is something that can give us mixture of products, but in these cases the mixtures that we are going to get are predictable and not too many, because the addition is only going to happen to 2 of the carbon atoms which are involved in the double bond, and there will be one major product and one minor product which normally can be separated. So this is a useful reaction. And in case we are looking at adding multiple number of halogen atoms, so let us say 2 halogen atoms, we can also add a halogen molecule instead of hydrogen halide. We can add a halogen molecule such as bromine across a double bond. In this case there are no issues. A bromine atom each gets added on to both the carbon atoms that are involved in the double bond. So therefore we get 1,2 dibromo compounds. We already discussed while discussing the classification of these compounds that if there are substitutions of carbon number 1 and carbon number 2, those are adjacent carbon atom, we call them as vicinal substitutions or vicinal halides in this case. So this particular reaction gives you vicinal dibromide from this. So this again is an efficient reaction, because we break bromine into 2 bromine molecule into 2 bromine atoms and add them across a double bond to get these compounds. So this is an effective reaction if you are looking for 1,2 disubstituted compounds. Now there is a simple application of this reaction which is normally done in smaller analytical labs, probably in the lab that you have in your schools or colleges. So what is done here, if you take bromine in water, it dissolves a little bit in water, so you get a brown solution of bromine in water. Now if you want to know whether a compound that you have is an alkene, whether it has a double bond, we can add bromine water to that, and what happens is if the compound that you are trying to analyze has double bonds, then bromine gets consumed because it adds across the double bonds, and as a result the reddish brown color of bromine disappears. So if you take bromine water which is colored and add into an alkene, the color of the bromine water disappears. So this can be used as a test for alkenes. So provided you do not have any other methods to detect the presence of alkenes, this can be used as a method. So this is normally used in your school labs and so on, so that you understand the chemistry and appreciate this particular reaction. Okay. So now in most of the methods that we have discussed so far, you would have seen that we were only talking mostly about the reactions of chlorines and iodine and bromine, because it is rather easy to prepare chloroalkanes and bromoalkanes, but once it comes to iodoalkanes and fluoroalkanes, the reactions have problem. Normally, for example, the reaction that we did in the presence of light, the reaction of chlorine and bromine works well. Iodine does not react normally under those conditions, and fluorine reacts violently. So, if the effort is to make fluoroalkanes or iodoalkanes, the number of possibilities are limited, whereas for chloroalkanes and bromoalkanes we have multiple number of methods, and most of the reactions work well because their reactivity falls in the range that is controllable by a chemist under the conditions that we can produce. Now, so therefore, if you are interested in preparing an iodoalkane, there is a simple way we can easily prepare them from other halogenated organic compounds. So, for example, if you take a chloroalkane or a bromoalkane and treat it with sodium iodide as it is shown in this particular reaction. So, if you take an Rx where X is chlorine or bromine and treat it with sodium iodide in acetone as the solvent, we would get the corresponding iodoalkane plus the sodium halide. Now, the whole reaction works better because sodium iodide is more soluble in acetone than sodium bromide or sodium chloride. So, therefore, once we take this reaction, we would have considerable amount of sodium iodide dissolved in acetone. So, if you add an alkyl bromide or an alkyl chloride into the solution, the reaction happens and the sodium chloride or sodium bromide that comes out would start to precipitate. So, the reaction is always running in the forward direction as suggested by Le Chatelier's principle, and therefore, we can easily prepare iodoalkanes using this method. This reaction has a name for those who are interested in names. This is called Finkelstein reaction. So, Finkelstein reaction is nothing but an easy preparation of iodoalkanes from chloroalkanes or bromoalkanes using acetone as a solvent. Using a similar method, using a rather parallel method, we could also make fluoroalkynes starting from chloroalkanes or bromoalkanes. So, in this case what we use is certain metal salts of fluorine where the metal has a better affinity for chlorine and bromine. So, such examples include silver, of course, then it has mercury, cobalt or antimony. So, in the case of these metals, what actually happens is the corresponding bromides and chlorides are more stable. So, once we treat them with an alkyl halide or an alkyl chloride or an alkyl bromide, the reaction proceeds by the formation of corresponding metal bromide or metal chlorides. I have written metal bromide here assuming that what I take is a bromide, or a metal chloride plus the corresponding fluoroalkane. So, this again is an exchange reaction. So, these two reactions that I have discussed now on this particular section are halogen exchange reaction, one where a chlorine or bromine is exchanged with sodium iodide, and another one is a chlorine or bromine exchanged with a fluoride of certain metals that have higher affinity for bromides and chlorides. So, that reaction again has a name, it is called Schwarz reaction, for those who would like to remember these reactions by their name. Okay. So, this so much about the reactions of haloalkanes. Now, we would go ahead and start discussing about the reactions of haloarenes. So, I have already mentioned that the synthesis of haloarenes are slightly different from the synthesis of haloalkanes. Even their reactivity patterns are different. This is largely because in a haloarene, the carbon halogen bond is through an sp2 hybridized carbon atom. Not only that, this sp2 hybridized carbon atom forms a ring. So, it has its geometrical constraints, so that it cannot give a lot of other reactions that alkyl halides can give. So, therefore, there are differences in their reactivity, and therefore, the preparation methods also have to be slightly different. So, one of the simplest methods that one can think about when we talk about aromatic compounds is their synthesis through electrophilic substitution reactions. So, I have a simple example here. So, I have taken an alkyl substituted benzene. So, when an alkyl substituted benzene is treated with X2, so X2 you will find that again in this case is chlorine or bromine most likely. So, when it is treated with a halogen in the presence of Fe, so in the presence of iron under dark conditions, because you do not want any photochemical reactions to happen. So, when it is done under dark conditions with no light involved, what iron does in this case, what Fe does is it first reacts with X2 to give you FeX3, the corresponding trihalide. Now, this FeX3 acts as a Lewis acid and it breaks additional number of halogen atoms. So, what exactly happens, I might be able to draw it for you. So, what happens here is you get an FeX3 which then reacts with X2 further to give you ideally an FeX3 bonded to an X through Fe with a negative charge plus an X positive. So, the X positive, so you are effectively creating a halogen, positively charged halogen atom in this case. This is formed because FeX3 that is formed from X2 and Fe can act as a Lewis acid. Now, this X plus is an electrophile. So, electrophile is something that has a liking for negatively charged species, something that has a liking for electrons. So, this X plus can then react with the aromatic compound and form a positively charged aromatic species here. So, the aromatic ring breaks down and it is no more aromatic, it forms a positively charged species, cation, and from this we lose an H plus and a double bond is reinstated to give us the corresponding haloarene. So, this reaction, as you would see, works through the formation of a cation, and the cation is formed when an electrophilic halogen ion, and halogen cation is reacting with the aromatic ring, forming a cation, and then it removes a proton, giving us finally the haloarene. And this reaction again works well with bromine and chlorine. So, you would find that when there is an R group already present on the aromatic ring, the X can be on any of these carbon atoms. It can be here as I have shown here, or on any of the other carbon atoms too. But the position of the newly formed bond actually depends on the nature of the substituent that is already present. So, for simple alkyl substituted aromatic compounds, the preferential formation would be on either on the para position or on the ortho position to the alkyl group. So, you already know that alkyl groups are ortho para directing, so that results in substitutions on ortho or para position. It does not matter even if you get mixtures, because these mixtures have different physical properties, so they can be separated by various methods that are available to a chemist to separate mixtures of organic compounds. Now, once again I will come back to the point that chlorine and bromine reacts better for this class of reactions and gives us bromoarenes and chloroarenes better. What happens with iodine is the byproduct of this particular reaction you would see is, so if I have to write the byproduct of this reaction, the byproduct is the corresponding hydrogen halide. So, you get HX as a byproduct. So, when the reaction is done with iodine, the byproduct is HI. So, HI is not a stable compound, so it is always in equilibrium with hydrogen and iodine. So, what happens is the reaction could go backwards. So, therefore, whenever we do this reaction with iodine, we would not be able to control the reaction and get an iodoarene as the final product, because the product might undergo a reversible reaction, giving us back the aromatic compound plus I2. So, therefore, what has to be done is, if an iodoarene has to be prepared, we make sure that the HI that is formed is somehow consumed. There are various methods to do that. One of them is to oxidize HI to a hypervalent iodine species so that the reaction does not go back, or the other thing is to do is, HI is an acid as you know. So, if you use a base, then HI gets neutralized and then we form the corresponding metal iodide, which would also make sure that the reaction does not go backwards. However, the reaction cannot be done for fluorine because we would have absolutely no control. Fluorine reacts extremely fast and extremely violently, so we will end up having mixtures of aromatic compounds having multiple number of fluorine atoms, and then their purification or isolation becomes difficult. So, the preparation of fluoroarenes is not possible using this particular method. Okay. Now, I will talk to one of the more controlled reaction for the preparation of these compounds, where we would have an absolute control over where exactly the halogen atom is going to be formed. And this method can also be used for the preparation of not only chloro and bromo arenes, but also for the preparation of fluoro and iodoarenes as well. Okay. So, the reaction starts from a primary amine. So, when a primary amino group NH2 is attached to benzene, it is called aniline. It is a primary amine as you know, because nitrogen is attached only to one group, one aryl or alkyl group. Those are primary amines. So, I take a primary aromatic amine and treat it with sodium nitrite and HX, where HX is an acid. So, this generally is hydrochloric or hydrobromic acid, as one would assume. It can also be H2SO4 or any of the acids that can give H plus. So, what happens under these conditions, when sodium nitrite is treated with a hydrohalic acid or sulfuric acid, it generates HNO2, which is nitrous acid. So, NaNO2 gets changed into HNO2. So, we do not normally start with a solution of HNO2, instead we prepare HNO2 starting from NaNO2 and an acid. So, now once you have access to nitrous acid, what happens is nitrous acid would react with the primary amine and give us something called as the diazonium halides. So, in this case, because we started with aniline, we get benzene diazonium halide, where X corresponds to the anion that was present in the acid that is used. So, if you use HCl, it would be benzene diazonium chloride. If you use HBr, it would be benzene diazonium bromide, and if it is sulfuric acid, we get benzene diazonium hydrogen sulfate and so on. So, we get a benzene diazonium salt where there is an aromatic ring that is attached to a nitrogen molecule with a positive charge. It is not just one nitrogen, there are two nitrogen atoms. So, what it does is this particular bond here can be cleaved quite easily. So, the carbon nitrogen bond can cleave, and an N2 molecule, you know, nitrogen molecule is a very stable molecule, that is why we have it in the atmosphere so much, because nitrogen molecule can easily leave out from various organic compounds because it forms a very stable species. So, in this case the benzene diazonium halide that is formed would break down and give us an N2 plus the corresponding cationic aromatic species. Now, this can be trapped with various number of nucleophiles, or some of these reactions also follow radical mechanisms. So, one particular application is when you take this benzene diazonium halide and treat it with a cuprous salt such as Cu2x2. So, this can also be written as Cux, there is no problem, where X is normally chlorine or bromine, then we get the corresponding haloarene plus nitrogen. So, the reaction proceeds this way. We already have an aryl diazonium halide, you can see an X minus formed there. So, when it is treated with Cu2x2 or Cux in short, it gives us the corresponding haloarene plus nitrogen. Now, the interesting point here is this X that is replacing here can be either one that is attached to copper or the one that is present as the anion along with diazonium salt. So, normally if you want a chloride, it is better to start with an aromatic diazonium chloride. If you want a bromide, it is better to start with an aromatic diazonium bromide and so on. Now, the reaction with Cu2x2 normally proceeds through a radical mechanism. The mechanism is quite complex. Copper, the presence of copper 1 metal ion in this case is to make sure that this reaction happens quite feasibly. These two reactions which can give us chloro or bromo arenes are called Sandmeyer's reaction. So, Sandmeyer's reaction is the preparation of chlorobenzene or bromobenzene or chloroarene or bromoarene starting from the corresponding primary amines through their benzene diazonium salts using a cuprous halide as the reagent for doing this conversion. Okay. Now, I said that this method can also be used for the preparation of iodoarenes as well as fluoroarenes, but in these cases we do not need the intermediacy of a cuprous salt. We can directly take a benzene diazonium salt, benzene diazonium halide, and treat it with potassium iodide. So, in this case we would get the potassium halide, where X being the one that was associated with the diazonium salt as an anion. So, that comes out along with the nitrogen molecule and we get the corresponding iodobenzene as the product. So, in this case, because I have used benzene, I get iodobenzene as the product. So, this reaction does not require copper, it is directly treating an I minus with the diazonium salt to get this reaction. Interestingly, this reaction also proceeds through a radical mechanism if you look carefully into the mechanism, but it can also be treated as a simple reaction where an N2 molecule goes out generating an aryl cation that reacts with I minus to give you an iodoarene. Now, the preparation of the corresponding fluoroarenes from diazonium salts is more straightforward, but it would require that we use certain anionic species such as tetrafluoroborate or hexafluorophosphate. So, these are boron and phosphorus salt where one extra fluorine is attached to both boron and phosphorus, giving us this anionic species BF4 minus, which is called as tetrafluoroborate, or PF6 minus, which is hexafluorophosphate. So, when the diazonium salt has these anions as the counter anions, once we heat them, what happens is nitrogen molecule is liberated from the species, and while that happens, this extra fluorine atom that is attached to boron or phosphorus gets added on to the aryl cation, giving us fluoroarenes. and the byproducts that are formed will be nitrogen molecule plus BF3 or PF5 depending on which salt we have started with. So, this method, as you can see, is quite efficient in the fact that this can be used for the preparation of both iodo and fluoro arenes, unlike some of the other methods which are limited to the synthesis of chloro or bromo compounds. So, now with this we have a fairly good idea about how some of these haloalkanes or haloarenes can be prepared. So, once we know how to classify them, we know how to name them, we know how to prepare them, now it is time that we look at what are their properties and how they can be used. So, now going through the physical properties of organohalogen compounds, I'll start off with alkyl halides. So, most of the alkyl halides are colorless. So, they do not have anything that can absorb light. So, as a result simple alkyl halides, if you take, they are colorless. However, bromides and iodides, if you keep them for a long time, carbon bromine and carbon iodine bonds are not very strong. We have already seen that in the previous class that carbon bromine and carbon iodine bonds are weak, they do not have a very high bond energy. So, therefore, once they are exposed to light or once they are kept under a condition where they are being heated, over a period of time those bonds can break, resulting in the formation of bromine or iodine. So, these colorless compounds would slowly start to get this brown darker colors. So, effectively they are colorless, but they could get color if they start to decompose. Now, most of the alkyl halides that are gaseous or that has a high vapor pressure, they have a sweet smell. So, if you smell them, you would feel that they are good to smell. Even chloroform, which is known to be not a good thing to smell, has a pleasantly sweet smell once you inhale them in smaller amounts. And in comparison with the corresponding not even the corresponding hydrocarbon. So, if you take a hydrocarbon with a particular molecular weight, let us say 100, and if you compare it with a haloalkane which also has a molecular weight of roughly around 100, you would always find that the haloalkane has a higher boiling point than the corresponding hydrocarbon. It is because we saw that the carbon halogen bond is polarized, and because of polarization they do have better intermolecular interaction. So, even if they are in solutions, even if they are in by themselves as a liquid, you would find that they have better intermolecular interactions through dipolar interactions or van der Waals interactions and so on. So, they have higher boiling points than the hydrocarbons of exactly the same molecular weight or nearly the same molecular weight. Now, boiling points of alkyl halides of course increases in the order from fluorine to fluoro compounds to iodo compounds, or they decrease in the order Ri, as I have given here, Ri greater than Rbr, greater than Rcl, greater than Rf. So, this is the order in which their boiling points vary. Of course, when you have these larger atoms present in them, their dipole moments and their van der Waals interaction, which is also associated with the surface area of these molecules, are higher. So, they have better intermolecular interactions. So, normally iodides would have a higher boiling point than bromides, chlorides or fluorides. Now, if we take isomers of this compound, so let us say we take a linear isomer and a highly branched isomer. So, the linear isomers have better intermolecular interaction and that results in higher boiling points for them. So, here I have an example of bromobutane. So, if we take normal bromobutane, that is 1 bromobutane, it has a boiling point of 375 Kelvin, whereas if I take tertiary-butyl bromide, it has a boiling point of 346. So, you can see that there is a variation, and the variation is in favor, and the highest values are in favor of the linear chains which do have better intermolecular interactions holding them together. So, boiling points are also reflected in that particular thing. Now, if we talk about haloarenes, not much general information that we can take home and keep in our memory and use, but it is okay to say that isomeric haloarenes have similar boiling points. So, their boiling points are normally similar, but if we take disubstituted compounds, that if we assume that there are 2 substitutions present in them, then normally the para isomers can be stacked better in crystals. So, therefore, they do have higher melting point, but their boiling points are still comparable with that of the other isomers. So, here is an example of dichlorobenzene. So, if you look at various dichlorobenzenes, you would find that for ortho, meta and para, the boiling points are nearly the same. So, there is nothing that distinguishes them too much. So, although there is minor differences, it is not something that we can that is worth remembering. So, it is just that they are all in the same range. However, once we talk about the melting points, while ortho and meta isomers have similar melting point, the para has a very high melting point. it is because the para, as you know, is very symmetric, so they can stack well in crystal structures. So they can be ordered well once we want to stack them in a crystal, and therefore as a result they do have better interactions in crystal structures and their melting points are normally higher. Then coming to the density of these molecules, bromo and iodo compounds are extremely dense. Chloro compounds are denser, but not so much if there is only one chlorine atom present, but polychloro compounds, even if we have just 2 chlorine atoms attached to a methyl group, so that is dichloromethane, you will find that it is more dense than water. So if you take water and these halogenated solvents that have either bromine or iodine or more than 1 chlorine atoms, they are more dense, so they would go under water. So if you take them in a bowl and make a mixture, you will find that water floats on top and these halogenated solvents are at the bottom. They are not necessarily soluble in water, so that is why they form 2 levels. So if you compare the amount of a halogenated compound dissolved in water, it is not normally very high. So the solubility of halogenated compounds in water are not so much, so they are not soluble. But they are soluble in most of the organic solvents because these are organic compounds and they can have very good interaction with organic molecules in general, so they dissolve well in organic solvents. What happens when we put them in water is held together by hydrogen bonding, and in a organohalogen compound or a haloalkane or a haloarene, you will find that there is nothing to do a hydrogen bonding with. So effectively we will have to break the hydrogen bondings that are formed in water molecules to dissolve these molecules in them. So that does not normally happen, so therefore they stay insoluble. Okay. So with this I would go into the chemical properties, rather reactions of haloalkanes. So here again I am not going to the reactions of haloalkanes and haloarenes in one go. Instead what I am going to do is discuss their reactions separately. So first I will discuss the reaction of haloalkanes, then I will go on to discuss the reaction of haloarenes. They do have different patterns of reaction. So starting with the reactions of haloalkanes, you will find that the most discussed reaction of a haloalkane, the one that is of most synthetic value to an organic chemist, is nucleophilic substitution reactions. So as the name suggests, these are substitution reactions. That means we have a compound, we substitute a part of this compound with something else, and because we are talking about haloalkanes, here the halogen atom is the one that is being substituted with something else. And what is it that is used for substituting the halogen atom is a nucleophile. So these are therefore called nucleophilic substitution reactions, as I have shown here. So nucleophile is a species that is normally negatively charged, that means they are anions, or they could also be neutral compounds with a high density of electrons present in them. So for example, if you take ammonia, which is a neutral molecule, but you know that there are lone pairs of electrons on nitrogen, so therefore ammonia is a nucleophile. It has those electrons that are ready to react with positively charged compounds. So nucleophile simply means something that likes nucleus, and nucleus is positively charged. So any species that likes to interact with positively charged nuclei are called as nucleophiles. So nucleophilic substitution reactions are substitution reactions where a nucleophile is used to replace a particular compound, a particular moiety from an organic molecule. So in this case we are talking about the reaction of haloalkanes. So have a look at the reaction that I have on the screen here. So you can see that there is a carbon X bond, and this bond we have already discussed while discussing the nature of carbon halogen bonds, that the carbon has a positive charge and the halogen has a negative charge. So this bond is polarized. Now the nucleophile with its negatively charged, with its electrons, would come and react with the positively charged carbon atom that is shown in blue here. So it would react with the carbon atom, giving us a new compound where we have a carbon nucleophile bond. So the nucleophile could be anything, we will look at examples soon. So it would form a new carbon nucleophile, and the halogen atom now completely takes the electrons that it was sharing with carbon and goes out as an X minus. So we had one negatively charged species to start with, that is a nucleophile, and in the product mixture we have a halide ion that has come out. So as I have said, nucleophiles can be anions or they can be neutral electron rich molecules. So they have to, if they are neutral, they have to be electron rich. If the molecule is not electron rich, then they cannot be a nucleophile. Okay. So now I told you that these are some of the most useful synthetic reactions. So to emphasize on that point, to demonstrate those points better, I have some examples here. So, a general reaction, general nucleophilic substitution reaction can be given as Rx, where X is the halogen atom, R is the alkyl group. When you treat with a nucleophilic reagent, we get Rnu and X comes out. So, this is the reaction, Rx can give you Rnu. So, now let us have a look at various nucleophilic reagents and the products that can be formed. So, if you use sodium hydroxide or potassium hydroxide, so these are anionic nucleophiles where sodium is positively charged and hydroxide is the negatively charged nucleophile. So, when we treat an alkyl halide with sodium hydroxide or potassium hydroxide, we would get the corresponding alcohol. So, the OH minus replaces the halogen atom. We can also do the same reaction with water. Water in this case is a nucleophile, but it is not an anionic nucleophile, it is a neutral molecule, but because of the presence of lone pairs on oxygen, it is a nucleophile. So, water can also do the same reaction, and in that case too we get alcohols as the product. We could also use a sodium alkoxide. So, that means you take methanol, replace the H from methanol and put a sodium there, then we get CH3O minus Na. So, these class of compounds are called alkoxides, which are the metal salts of alcohols. So, if you treat an metal alkoxide with an alkyl halide, there again sodium chloride, sodium bromide would come out, the corresponding sodium halide would come out, and we would get an OR attached to the alkyl group, and these are ethers. So, you would learn about these molecules in a different unit in your textbook. So, we would get ethers as the product. Similarly, I started off by telling about ammonia, which is a nucleophile. So, if you treat ammonia with an alkyl halide, we get the corresponding amine. So, HX comes out in these cases, ammonia is a neutral molecule. So, we get RNH2, an amine as the product. Now, in the second part of this table, in the second set of columns that I have here, I have rather interesting nucleophiles. So, first of them is potassium cyanide, KCN. So, potassium cyanide, you have already heard of that particular molecule, I am sure. So, when you treat potassium cyanide with a haloalkane, the product is an alkyl cyanide. It is also called nitriles. So, you get a nitrile as the product. So, an alkyl halide treating with cyanide minus, Cn minus, gives you the corresponding alkyl cyanide or nitrile, alkyl nitrile. So, now the same reaction, instead of potassium cyanide, if I do with silver cyanide, AgCN. So, you can see that the difference is only in the metal that is used. So, potassium cyanide or silver cyanide, but in this case the product is not a cyanide, it is an isocyanate, and you would also see that I have drawn it with an RNC, I have drawn it as RNC, not as RCN, and cyanide is Cn minus. So, if I have to draw how these nucleophiles look, I would be able to say that a cyanide anion is Cn minus. Now, the negative charge here is centered on the carbon atom. So, if I have to draw the cyanide anion, I will be able to draw this with a triple bond between carbon and nitrogen and a negative charge on the carbon atom. So, this normally is in it has another resonance structure that can be written like this, with a negative charge on nitrogen and the carbon having a lone pair. So, cyanide anion has these two particular forms in which they can be written. So, this is to say that the negative charge is either on carbon or on nitrogen. So, once we have cyanide anion reacting with an alkyl halide as a nucleophile, so the nucleophilicity of cyanide ion is in such a way that the most stable bond forms. So, generally a carbon-carbon bond is more stable to form. So, if you take cyanide anion and react with alkyl halide, we will always get the cyanide. But if silver cyanide is used, the silver cyanide bond, the carbon silver bond is not ionic. So, therefore, what happens is when we put in silver cyanide in a solution, the Ag plus and Cn minus does not come off. Instead, there is always this covalent bond between silver and carbon. So, it is partially covalent. So, silver always remains associated with the carbon atom. Therefore, the nitrogen atom at the other end of the cyanide anion would be able to react as a nucleophile. Nitrogen always has its lone pair. So, you can see that in this structure I have put this lone pairs on this one. So, let me just highlight those. So, you would find that I have these lone pairs on the nitrogen atom. So, if the silver atom is attached to the carbon atom strongly, then the lone pairs on nitrogen will start to react as the nucleophile, and as a result we get a product where the alkyl group is attached to the cyanide through nitrogen, and that is called an isocyanate or an isonitrile. So, with the same nucleophile, literal means for practical concepts we can assume that it is the same nucleophile, but it has two different centers of reaction, and these kind of nucleophiles are called ambident nucleophile. So, an ambident nucleophile is something that has a negative charge that is shared between two atoms of different kind. So, in this case a carbon and nitrogen. So, the reaction can be through the carbon atom or through the nitrogen atom depending on the reagents that are being used, or sometimes depending on the conditions that are being used. Another of that class is the nitrite anion. So, if I take potassium nitrate, which can be written as, again I will try to write that, a nitrate anion is O minus attached to nitrogen and an N plus O. So, this nitrogen has lone pairs. So, this potassium nitrate would be like this, with K plus associated with a negatively charged oxygen and then the NO group. Now, if I use KNO2 as a nucleophile, then it is always the minus charge on the oxygen that is acting as the nucleophilic atom, and it goes and forms a carbon oxygen bond. If I use silver nitrate, in that case the AgO bond remains strong. So, therefore, the reaction again, just like in the case of isocyanide, happens through the lone pairs that are present on nitrogen atom, and as a result the reaction would be happening from here. So, then we get a carbon nitrogen bond in the product, and those compounds are called nitroalkanes. So, if a carbon nitrogen bond is present in a compound that has NO2 as the substitution, then we call them as nitroalkanes, and in the other case they are alkyl nitrates. So, this table, as I have shown, just tells you how useful nucleophilic substitution reactions are, because we can use, not only that we can put various groups onto an alkyl group by doing nucleophilic substitution reactions, sometimes we can use the same class of nucleophiles but react them through different atoms and get different products. So, this is a very synthetically useful reaction. So, therefore, it is also important that we study this reaction in more detail. So, nucleophilic substitution reactions are very useful. So, let us have a closer look at them. So, there are two kinds of nucleophilic substitution reactions that we can do on a haloalkane. The first of its class is shown here, is a substitution nucleophilic bimolecular. So, this reaction is normally shown as SN2 reaction. So, SN2 means S stands for substitution, N stands for nucleophilic, and 2 stands for bimolecular. So, I have an equation here, a reaction sequence that is written here with structures. So, this pretty much sums up what exactly this reaction is. So, in the example that I have chosen, I have taken a hydroxide anion, which is the nucleophile, reacting with chloromethane. So, it is the carbon atom that is attached to 3 hydrogen atoms and a chlorine atom, and now the reaction proceeds in such a way that the hydroxide anion reacts with the carbon, forming an intermediate, forming a transition state that is not an intermediate, it is in one step. So, the whole reaction happens in one step, where initially the carbon chlorine bond starts to weaken and a carbon oxygen bond starts to form, and we get a transition state like this, which then collapses into products where a new carbon oxygen bond is formed and Cl minus comes out. Now, why do we call this as a bimolecular reaction? Is the so this whole mechanism can be summarized into a few points. So, I would read out those points for you. So, the reaction follows second order kinetics. So, if a nucleophilic substitution reaction follows second order kinetics, that means if the order of the reaction depends on the concentration of the haloalkane as well as on the concentration of the nucleophile, then that is a bimolecular reaction, that is an SN2 reaction. In other words, in an SN2 reaction, the rate of the reaction depends on the concentration of the nucleophile as well as the concentration of the haloalkane. It is a single step reaction, there are no intermediates formed, there is only a transition state. In the transition state, the carbon atom is bonded to the nucleophile and the halogen atom. So, in this case the halogen atom is called as a leaving group, because this is the group that leaves. So, the nucleophile, the carbon atom is bound equally to the nucleophile as well as the leaving group in the transition state of the reaction. And in the transition state, we can assume that the carbon atom is pentacoordinate, that means it has 5 atoms attached to it, 3 hydrogen atoms that we started with, which are present in the methyl group, then the chlorine atom and the nucleophile, all of them are bonded to carbon giving a pentacoordinate carbon atom, and also this reaction happens with inversion of configuration. So just to tell you what exactly do I mean by inversion of configuration, I would use some models to show you how this reaction works. So you can assume a haloalkane to be like this. So this is, let us assume that this is chloromethane, and imagine that the blue colored atom here. So this blue colored atom here that I have shown in this model is chlorine. Then the black one is carbon, and it is attached to 3 hydrogen atoms. So this is chloromethane for you. So you can see that this is tetrahedral. So if you look at the model, I can rotate it for you. So you feel that this is a tetrahedral carbon atom. All the bond angles are 109 degrees. So now how does a SN2 reaction happen is you would have this haloalkane, chloromethane in this case, then the hydroxide anion, which is red in color, starts to approach from the back side of the carbon chlorine bond. So always this attack in an SN2 reaction, the approach of the nucleophile is from the back side of the carbon halogen bond. So once it starts to approach from this direction, you would start to see that this particular bond between the halogen and the carbon atom starts to weaken. So this nucleophile approaches, it starts to form a bond. So as there is a new bond starting to form, this bond starts to weaken. And when this bond starts to weaken, what also happens is these 3 hydrogen atoms, which are slightly pointed in this direction, starts to flatten out. So we would reach a stage where the carbon atom is equally bonded to the blue atom, that is halogen, and the red atom, with all these 3 hydrogens being in one plane. So this is the pentacoordinate structure that I was talking about. So if you look at the screen again where I have this molecule, you will see that in this particular part, what I have is a planar species where there is 1 carbon atom and 3 hydrogen atoms attached. So you could also assume that in this particular carbon atom is sp2 hybridized with 3 hydrogen atoms in one plane, and there is a p orbital. Now let us assume that the nucleophile and the halogen atom are bonded to the 2 lobes of the p orbital. So that is how this transition state has to be viewed. And now, so this was our starting material. So what happens is the nucleophile comes from the backside, reacts with it, forms a new bond, and then we get a product that looks like this. So this was the starting material. We had chlorine on one side, and now the nucleophile has come, and it almost comes from the backside. So if the starting material looked like this, if the haloalkane looked like this, the product looks like this, with the new carbon oxygen bond being exactly in the opposite direction. So what you can imagine is, if you assume this to be an umbrella where I hold here, and this if you assume to be the part of the umbrella, after the reaction I get a product that looks like this. So this is as if your umbrella has undergone an inversion in wind. So this, therefore we normally say that a substitution nucleophilic bimolecular reaction happens with an inversion of configuration. This is as if an umbrella has inverted during the course of the reaction. So these are the main features of a nucleophilic substitution reaction. Now let us look at this reaction a little more closely. So what I have in this particular screen here, a methyl group, a halomethane, a haloethane, an isopropyl halide, and a tertiary butyl halide undergoing a reaction. So the point I want to stress here is, because substitution nucleophilic reaction has this very strange transition state where a carbon is attached to 5 different atoms. So in this transition state, the bulk around a carbon atom plays a lot of role, and also the approach of the nucleophile towards the carbon atom also is limited by what is present on the carbon atom. So if you look at a methyl group that I have in the first structure here, you see that a methyl has 3 hydrogen atoms, and when the nucleophile is approaching this, it only feels these 3 hydrogen atoms. Hydrogen atoms are extremely small, so the nucleophile has no problem in approaching this carbon atom and starting to form the new bond. Once I go into an ethyl group, the nucleophile almost approaches the same way, but one of the hydrogen atom is now replaced with a methyl group, with an alkyl group. So therefore the repulsion between the nitrogen and the alkyl group, the steric crowd that the nucleophile is starting to feel, is quite higher. So therefore the nucleophile will not be able to reach closely enough onto the carbon atom to form this bond very effectively. So as a result, this reaction is slower, and once I have an isopropyl group, there are 2 alkyl groups, so the reaction is even slower, and if I have tertiary butyl group, then there are 3 alkyl groups, so therefore the nucleophile cannot even approach the carbon atom. So these numbers that I have written here, so I have 30 written here, I have 1 here, I have 0.02 and a 0 written here. So these numbers actually represent the relative rates of this reaction. So if you assume that a methyl halide undergoes nucleophilic substitution with a rate of 30, the corresponding rate of an ethyl halide would be only 1, and that of an isopropyl halide is 0.02, and that of a tertiary butyl halide is just 0. So this tells you that the rate of these reactions are largely dependent on the bulkiness of the carbon atom, the bulkiness of the groups that are around a carbon atom, and the least substituted a carbon atom, and the rate of an SN2 reaction is faster, and as we keep on adding substitutions on this, the reaction becomes slower. So there are very many things that are associated with this SN2 reaction. It is a bimolecular reaction. It depends on the concentration of the nucleophile and also on the concentration of the alkyl halide that is being used. It depends on the structural features of the alkyl halide, because a bulkier alkyl halide will not be able to have an initial bond starting to form between the carbon and nucleophile. So therefore, primary alkyl halides react faster than secondary, which react faster than tertiary, and a methyl halide or a halomethane reacts the fastest because it does not have any sorts of steric crowding around the carbon atom, so it reacts the fastest. So these are the representative reactions. Now if you would also like to think about what kind of solvents can be used for this reaction, remember this particular point, that anything that can dissolve an anion can be a good solvent. So what we would need a solvent that can dissolve these anions. So normally polar solvents are required. Then we also do not want these anions to be highly solvated. So we do not want solvents that have hydrogens present in them, like alcohols for example. So normally polar aprotic solvents are the ones that are used for nucleophilic substitution reactions. So these are solvents that are polar but do not have a proton attached to an electronegative atom, so that the anion can be solvated. So we want solvents in which the nucleophile is rather bare and not at all solvated. So with this I would stop today, and we would continue to discuss the second class of nucleophilic substitution in the coming class and their stereochemical features as well. So thank you very much.